last talk for today. Talk is given by Kuba Wonsky, and it's on dynamic PageRank.
Thank you, Sebastian. Yeah, so this is joint work with Raj, Slobodan, Krzysztof, and Piotr. So far in this workshop, we've seen a lot of great talks with some deep algorithmic ideas. In some sense, this talk is going to be an exact opposite. Like what I'll be talking about is going to be quite simple, but I would like to use it as an opportunity to discuss some challenges in applying dynamic algorithm in practice, as well as also maybe discussing a problem which, at least in the dynamic version, I guess you don't often see studied in theory conferences. All right, so let's jump right in. Let me start by defining PageRank. So the input here is a directed graph. We assume that the out degree of each vertex is non-zero. You can deal with the other case as well, but let's ignore this for simplicity here. And we have a single parameter alpha, which is the jumping probability. And now to define PageRank, we define a Markov chain on the set of vertices of V with probability alpha over n. We jump to a random vertex and then otherwise with the remaining probability, we follow a uniformly random out edge of the vertex we're in. So if we write this in the matrix form, in this matrix, each entry has value alpha divided by n, plus for the entries which correspond to the edges, there is an additional term corresponding to following the edges. And the PageRank problem is simply to compute a stationary distribution of the Markov chain described this way. Now, for my talk, this definition is going to be completely irrelevant. I'm going to use one which is easier to use algorithmically, which is the following one. To compute PageRank, we do as follows. We pick a vertex V uniformly at random, and then we follow a PageRank walk from V. And now PageRank walk, I wrote it in bold because it's a term I'm going to use a lot throughout this talk. To define a PageRank walk, I first pick K from geometric distribution with parameter alpha, and then I run a uniformly random walk from V of length K. So basically, I start in K with probability alpha. I stop immediately. With the remaining probability, I take a random out edge. At that point, I stop with probability alpha. And if I don't stop, I follow a uniformly random out edge, and so on. So this is what I get from this geometric distribution. And now PageRank is also a probability distribution pi, such that P of V is the probability that the walk defined this way stops in V. Any questions?
Is it alpha or alpha times n? I mean, to be consistent with the... Is it alpha here, or is that consistent with the previous definition?
Yes, I think it's consistent here. Here I wanted alphas. I wanted each row and row or column. Yeah, I mean, I wanted each row and column to sum to alpha here.
Yes.
Okay. Does this make sense? Okay. So
no, but according to this definition, the longs are fairly long, right? Because you only jump with probability alpha over n.
Yes. Okay. So I think there is a typo here with probably alpha jump to a random vertex. Sorry.
Okay,
yeah, you're right.
Thanks.
So, yeah, everything else was good. Thanks. Yeah. So now this makes sense right now, right? Okay. Good. More questions? Okay, so I guess we can continue. And now dynamic PageRank is exactly what you may expect. We have a graph, and it's undergoing changes. We can add edges, we can delete edges, and we'd like to explicitly maintain an approximate PageRank vector pi. Now, for this talk, I'm going to assume it's explicit maintenance. It's actually the same as saying that every update outputs a list of changes to the PageRank vector. And this is a very convenient interface because, for example, if I would like to, I can maintain, using this output, I can maintain the top 1% of vertices with the largest PageRanks, or some other statistics on PageRanks. If I were just given a query interface, it would be extremely difficult to tell what has changed after a particular insertion or deletion. And then I will be assuming that all the algorithms must have this kind of problem. And then again, following standard terminology, we say an algorithm is fully dynamic if it supports both additions and deletions, incremental if we can only add edges, and decremental if edges can only be deleted. Nothing very surprising here. Yes?
Why is this formulated only with additions and deletions of edges? Why don't you delete and add vertices?
I think it's in a sense something that does not change. Well, okay, for PageRank, okay, it's a good question. Like usually, you can have like a pool of vertices right on the side that you can just add preemptively to the graph just in case you need them in the future. And adding a vertex is equivalent to just grabbing an unused vertex so far and connecting it to your graph. I think it's actually the same here if you play with the probabilities. So I think you can do that, but it's just like a technical annoyance. It's not something that changes the problem in a fundamental way. So this is where the core of the problem lies. Okay. So now time for our results. The first one is the lower bound, showing that for any number n, any graph size, any incremental algorithm which processes a linear number of insertions to an n-vertex graph and maintains a constant factor approximate PageRank must run in essentially quadratic time. This basically means that if we want to explicitly maintain PageRank, it's hopeless. We need quadratic time. At the same time, you can compute PageRank from scratch in essentially n polylog time. So this almost matches the upper bound. And it actually resolves an open question that was raised some 13 years back. This question was partially addressed before. There were some impossibility results for this particular algorithm. And we show that it actually holds for any algorithm that maintains PageRank explicitly. As you may guess, the proof just shows a graph and an insertion sequence where the number of changes to the PageRank vector is almost quadratic. And the same thing holds for decremental algorithms. Not very surprising because you can play the whole update sequence backwards and you get the very same result.
So two approximate, you mean every component is?
Yes, it's a component-wise to approximation.
But
yes.
there could be other kinds of approximations.
Yes, that's coming up next slide.
Okay.
Yes, so now, since we know that maintaining constant factor approximate solution is hard, we turn our attention to other notions of approximation. So multiplicative C approximation is what I now define, having it used on the previous slide. So it's just a component-wise C approximation of the PageRank vector. And then an additive C approximation is just saying that the L1 error or L1 difference between the exact PageRank and my solution is at most C. So we know that multiplicative C approximation is hard. We all know what's coming up now. We show that maintaining additive approximation is actually doable. For any constant epsilon, we can show both incremental and decremental algorithms which maintain epsilon additive approximation to PageRank and run in near linear total time. Now, the caveat is that the exponent in the polylog depends both on alpha. That's not too bad because like alpha is typically set close to 1/2, but also on epsilon, and that's actually worse because we may want epsilon to be pretty small.
Yeah, I mean, okay, the scale of epsilon, right? Don't I want the probability of a given page to be very, very small?
Sorry, so can you repeat?
If I have n pages overall, the number you're trying to, if all pages were equally valid, then we'd want something like 1/n.
But this is additive, right? So
right.
So yes, I mean, if you want to have some kind of multiplicative guarantee, yes, like large epsilon means that we may be very much wrong for those small values, unless we make it extremely small. Yes, so this is correct. it turns out that actually PageRank of any vertex is at least alpha divided by n. There is a lower bound. And then on the other hand, in applications, we're mostly interested in vertices of large PageRank, so which to some extent motivates studying also this notion. But yeah, it is weaker, especially for the vertices with small PageRank values.
All right, I guess. So this raises the question then, can you have some kind of mix where for the pages of very small PageRank, they still stay very, very small, but with the ones that are larger, you can tolerate an epsilon error.
Mm-hmm. Yeah, the lower bound we show, I think it actually, yeah, I think it does not rule out, I think, those cases. I think it's like we show like that many vertices would oscillate between constant and like 1 over polylog PageRank. So I think, yes, this is actually a good question. It's not ruled out as far, at least by our lower bound. All right, and now a third result. Third result relies on a batch recomputation approach. A batch recomputation approach is what I define here. So it's an algorithm which first computes an initial PageRank vector and then does nothing for some number of updates. It just reuses this initial vector for some time. And only after sufficiently many updates accumulate, it recomputes PageRank from scratch. So it's a very crude approach to solving PageRank. It's almost like solving almost like solving the problem from scratch, except that we do nothing for many steps. So sounds like a very bad idea, except that it's actually not, to our surprise. So we can both show good theory and empirical results for this particular algorithm. So we can show for a batch recomputation algorithm that I'm going to specify in detail later, we can show that it can handle any sequence of random updates in almost linear time in both incremental and decremental settings, as well as if none of the PageRank is too large, we can also maintain PageRank in a fully dynamic setting in time roughly O of b in each step if each PageRank is at most beta over n. And this algorithm is extremely efficient in practice, which to some extent is like a sad information to like people working on dynamic algorithms, because we see that now we take a very simple approach, and it then turns out to outperform perhaps more clever approaches that were considered before. Yes?
This is probably too soon to ask this question because
We'll probably get to it later. So you're doing this on very large graphs, and so isn't there what about like, is there a problem with I guess what model are you? I mean, there's like a cache issue with all the. I mean, the random. I don't know how. I was curious. Will you get to how you're implementing this stuff?
Yes, I mean this one. Yeah, I will talk about how we do that later.
Yeah.
And then
Okay.
also like
I
try to explain what's happening that why this is performing actually pretty well.
Yeah. Thanks.
I see Shushan and John.
Good.
I could imagine that computes an initial PageRank vector on real data sets. Maybe taking the last PageRank vector that you computed would be a good starting point. And I'm just wondering, as an order of magnitude, how much faster does that converge than if you took, say, a random PageRank vector?
Sorry, I'm not following.
Well,
what is random
when you say
PageRank vector?
computes an initial PageRank vector.
Yeah, so this means that we just compute an almost exact PageRank using power method in practice, right?
Okay.
Any method.
Well, is there any consideration at all of not starting with a good seed? Like, I'm presuming starting with a good seed is like super crucial in making this conversion.
Yeah, but it's also cheap. So
Okay.
I mean, it's cheap enough that we can do it. So why not use a good solution from start? I think that's the thing.
It always converges with 1 over alpha iterations wherever you start from, so it doesn't matter.
It doesn't matter. Okay. So I don't know what the theory is.
Oh, I see. So you're saying for the iterative process of starting the I think we actually start with uniform and then do a bunch of power iterations. We didn't actually. So the empirical results hold even without really optimizing the recomputation algorithm. We use a very simple implementation. We did not even tune that. And even so, it was working well. But yeah, we'll get to that later.
So just to understand this, so you're not doing personal PageRank?
No, it's only for PageRank.
Okay, right, because personal PageRank could be much larger than order 1 over n, right?
Yes,
Like,
personal PageRank, it does not have some of nice properties. Yeah, this is for PageRank, which is a slightly simpler problem.
okay, thank you.
Okay, let's move on. So we're done with the green section. So now let's move to the blue one. So let's review some prior work, and then we'll discuss our result in more detail. And we'll then wrap up and show some other problems. Okay, so now this slide is also very important. We're going to use this algorithm a lot to explain what's going on later. So please make sure you see what's happening and ask me questions if something is not clear. So we would like to compute PageRank via random walk sampling. This is an algorithmic version of the definition that I provided. So we have 3 parameters in addition to alpha, which defines the problem we want to solve. We have two parameters of the algorithm. So we have epsilon and an integer L. And so what we'll do is we'll set compute R, which is roughly log n. And then we'll sample our PageRank walks starting from each vertex of G. And then we remove all walks longer than L hops. This step is not really important if we would just want to solve a static problem, but it will become important once we make this algorithm dynamic. And then we do a simple thing. For each vertex V, we just compute the number of walks that stop at this vertex, and then we turn this into a probability distribution. So we just normalize just to get a probability distribution pi. You can show that this computes a multiplicative 1 plus epsilon approximation of PageRank with high probability. Is the algorithm clear? OK. So just a note, this algorithm computes 9 log n divided by alpha squared times epsilon random walks per vertex. So from theory point of view, this is great. This is just log n, which we typically consider a small number. But in practice, if you start plugging in actual values, you can see that this easily goes in thousands. And to justify the picture, this is actually the very same picture, just rotated, just to illustrate how looking at the same thing from different perspectives may lead to different observations. OK, so now how do we make this algorithm dynamic? This was done in a paper in VLDB 2010 by Bahmani, Choudhury, and Goel. I'm going to refer to this algorithm as BCG for short. And the algorithm is just a direct dynamization of the previous algorithm. We will maintain a collection of PageRank walks, and we will update that whenever needed. So for example, when we delete an edge, we just, well, what does it break? It breaks only the random walks that use that particular edge, and we have to resample them. And so there are some important caveats. For each resampled walk, we must make sure that the length of this walk stays the same. Otherwise, this would introduce a bias. So we do not resample the walk length from geometric distribution. We keep it what it was. And we only resample the part of the walk after x. Again, if we resample the entire walk, which is what some papers have suggested, this does introduce biases. And actually, we also tested that it is clearly visible in practice, even more than what we thought would be the case.
Just to be clear, you have to maintain all the walks that go through an edge?
Yes, so actually, yes. For each edge, we will have to maintain exactly every single walk that goes into it, so that when the edge is deleted, we can access those walks efficiently. And then when an edge is added, we also do an easy thing. For every walk, if we add an edge from x to y, for every walk going through x, we reroute it to use this new edge with probability 1 divided by the new degree of x. And again, there are some caveats. The lengths of the walks need to stay the same. And also, there's a tricky case when a walk visits x multiple times. You need to play with the probabilities, but yeah, it's not too difficult to get it right. So, and then this way, we just, at every step, we maintain a uniform and independent distribution of random walks. Of course, I'm assuming oblivious adversary here. Adaptive adversaries, yeah, we will briefly mention towards the end. And so this essentially inherits the algorithm, the guarantees of the static algorithm in terms of approximation. So here's a theorem. It maintains 1 plus epsilon approximation of PageRank. And if all of the edge deletions are uniformly random, the total update time is n(r) is roughly n times r. R is just a log, so this is n polylog n. It's not even, yeah, it can be even sublinear if the number of edges is large enough. Yeah, this is the total time of handling all updates for any sequence of random edge deletions.
Of like, excuse me? All deletions.
Yeah, like if you start with any graph, delete all the edges in random order, this is the total update time you get. Yeah. So a proof idea, it actually fits in the remaining part of the slide. There are n times r random walks, each of expected length 1 over alpha. And so when I delete a random edge, I will likely not hit a lot of them. I mean, this is perfectly uniformly random. I will hit this many walks in expectation, which is a small number, right? If m is large, this can be subconstant, and only this small number of walks needs to be rerouted. Rerouting a single walk takes time proportional to its length, so it's also fast. And this way we get the bound. All right. There is also a second algorithm, but in the interest of time, let me skip that. I will not be using that later. It also has a dynamic version. But yeah, let's move on to our results. So the first one is the lower bound, which I did mention. I think I will also, I will skip the construction. It's also maybe a bit less relevant. Let's go to algorithms. So I showed you before, this was result number 2, that if we assume that if we are interested in bounding L1 error, we can do that in polylog amortized update time. Here is the corresponding algorithm. It's adapted again from the static algorithm that I showed before. We sample that many PageRank walks per vertex. Each length is chosen from this distribution, but now we remove all walks longer than this much. This is a constant depending on alpha and epsilon, and then everything else follows as before. So I'm running the static algorithm, except that I'm throwing away all the walks that are longer than constant. So natural question is, how badly do I mess up the approximation? In particular, this is not even a probability distribution, like because out of that many sampled walks, I only count those that were actually run. This does not add up to 1. Sorry, this should say the number of walks that ended V. Sorry. This formulation is also can also be made to work, but yeah, but the one I'm using for this talk is we count the number of walks that end at vertex V. And so the question is, how much error do I introduce by throwing away all the longer walks? Well, it's easy to compute. The probability that the walk deleted in step 3 is more than L is at most that much from geometric distribution, and that's just epsilon over 2. So from all the walks that I run, I'm going to delete an epsilon over 2 fraction of them. So my L1 error is only going to increase by epsilon over 2 factor. So I'm not introducing a lot of error by limiting the walk lengths. And as we will see on the next slide, having walks of constant length makes their maintenance easier. Why is that? Well, turns out that if we have walks of constant length, maintaining them under, say, deletions or insertions, I think I'm using insertions on this slide, it's all symmetric, implies low running time. So let's take a look at a specific vertex V, and let's assume that outgoing edges are being added to this vertex. So when the ith outgoing edge is added to this vertex, the walk is rerouted with probability I. So from a harmonic sum argument, the number of reroutings of this walk for this particular vertex is going to be at most logarithmic, right? So I have a vertex. This only outgoing edge was chosen. I add some edges, but only say when the third edge is being when the second edge is being added, I reroute it with probability half. When the third edge is being added, I reroute the walk with probability third, and so on, and it all sums up to log n. So for a single hop, the probability of the number of reroutings is log n, and then you can show that a walk of length L is rerouted in expectation log to L n times, which gives me the bound for the algorithm. So from theory point of view, this all works. Now, as you may imagine, this exponent is terribly bad, and we will actually see that that even though this is technically polylog, this algorithm is not visibly faster than say not even limiting the walk length. So that was algorithm 2, and now perhaps the simplest algorithm, which is the batch recomputation. Here is what I mean by batch recomputation in more detail. So the algorithm maintains just two things, my graph and a single integer t, which just tells me how many more operations until I recompute everything from scratch. To initialize the algorithm, I call recompute. So I compute approximate PageRank of G. In our experiments, we were just using power methods, but you can also use random walk sampling if you're interested in theory bounds. And then after that, I say that I would like to recompute after I delete a constant factor of all the edges. And I'm going to use a parameter gamma to control for that. And now, when I add or delete an edge, I will do nothing. Well, I will update the graph just to record that the update happened. I will decrease t and only do some non-trivial recomputation once I reach the point where I want to recompute from scratch. That's it. So the philosophical question if this is even a dynamic algorithm or a static one that we run periodically. But I mean, it's well, in some sense, we are able to show bounds better than running the PageRank after every update. Is the algorithm clear? Okay. So now let's try to analyze this approach. Why does this? How can we bound the theoretical properties? So let's look again at the algorithm that we started with, the one that maintains a collection of random walks. So now when we delete a random edge, we were saying, well, this random edge deletion only hit a small fraction of random walks. So now, previously I was saying I will reroute them, but I can also say I will do nothing, and my error will not increase by a lot in expectation. So it's a very similar argument. I'm saying that a random deletion, if I totally ignore it, will in expectation not change my PageRank by a lot, and the proof goes by this random walk sampling algorithm, right? We affect few of the random walks, and so naturally we cannot change the result of that random walk based algorithm in a significant way. And it's both simple and tricky. If it's not clear, I'm happy to elaborate. But if there are questions, please stop me. So if we do nothing, the L1 error under a random deletion increases by just 1 over m times alpha, so by a very tiny amount. And so we don't need to do anything until a constant fraction of edges are deleted from the graph. Yes, John?
I'm just wondering about the first one. Is there some underlying assumption that the degrees are not that different? So here's why like here's a point I'm not sure about. So if I have a graph where the degrees are really off, right? Like so let's just say you have a star and one of the ends of the star there's a single vertex. So this cut edge, or I mean all of them are cut edges, but this extra edge that a single vertex is hanging off of, 1 by n fraction, or let's say a clique and a single one, 1 by n fraction of the random walks will go through this edge. But if you have a clique, every other edge will get very small, 1 over n squared fraction of the edges of the random walks.
Yes, but
So deleting a random edge.
but I think the difference between these two cases is that the number of edges varies a lot, right, between these two.
No, so okay, sorry. I think I switched my example. So let's say you have a clique, n squared, and then you take an extra edge and attach just an isolated vertex. For this extra edge, you have all the random walks out of the new vertex coming, right? So that's 1 by n fraction of the random walks.
Yes.
That's much more than 1 over m.
Yes, but in your example, let's see. But that edge is very unlikely to be picked, right? Because, I mean, very unlikely. It's 1 out of n squared edges, right?
Right, but it affects. Oh, I see. Okay, thank you.
Yeah. So, any more questions?
So the bug that you initially mentioned, it's not on the random updates, right? So this is just for the intuition?
Sorry, the what?
The theorem that you stated at the beginning of the
No, there are two parts. This is under random updates, and then there is also another one under arbitrary updates. Yeah, so if we have random updates, a single update cannot change my PageRank much. So if I do nothing, my solution is still pretty good, and I can show that the number of batch recomputations is just constant across my whole stream, and so I get like the running time of m polylog n. This is under random updates, and under adversarial updates, if I say that the PageRank of a vertex is at most beta over n, I can show that at most beta polylog n PageRank walks leave every vertex, and so again. That many PageRank walks can use any out edge of this vertex. So again, deleting a single edge cannot affect a lot of walks, and so my PageRank will not change by much, and I get the same update time times beta. Okay, so that was the theoretical analysis. But now the interesting part, and I see I need to speed up, is our empirical results. So we implemented those algorithms in C++. We used temporal graph data sets from Snap, which means we had directed graphs, and the edges all had like some timestamp attached to them, which we used to define the order of adding or deleting edges. Actually, for the experiment, we were just deleting edges. And then we considered 2 orders of edge deletions, random, and also the temporal one, which came with the data set. And we looked at 2 algorithms. There is the BCG algorithm, which maintains PageRank walks with 2 parameters, the number of walks we sample per vertex, and a cap on the length of the random walk. We saw that, in theory at least, capping random walk lengths helps. And then simple PageRank is just the batch recomputation approach. What we parameterize it with is just the number of recomputations we do. All right. So for the first experiments, we were looking at what is the effect of limiting walk lengths. So we maintain PageRank walks using the BCG algorithm. We delete edges in random order. On the x-axis, we have time. On the y-axis, we have the error. So we want to be in the bottom left corner. And then we vary both parameters, the number of walks and the maximum length of a walk. So each curve here is what happens to the error time trade-off as we increase the allowed length of each random walk. So basically, this means that we cap the length of each random walk at 1, and the points here mean that we cap the length of each random walk at say 128. And essentially, the best error to time trade-off is when we do not cap the walk length at all. So this means that actually, out of these 2 parameters, tuning the number of walks gives us a better trade-off between error and time than limiting walk length. It's a sad realization that our theory for that part did not lead us to something that we can see in any way in practice. So that was like a negative result. And then we also see that we need more than 2,000 walks in order to get L1 error of 1%. And now, a second thing is that we saw that the batch recomputation is very efficient under L1 error. Now, we compared this BCG and simple PageRank algorithms. Now, since limiting walk lengths did not prove to be useful, we just tuned the number of walks sampled for the BCG algorithm and the number of recomputations for the batch recomputation approach. We consider 2 order of edge deletions, and we plot the results. So these are the different trade-offs we get by tuning the number of batch recomputations for the simple algorithm. And this is the different results we get if we tune the number of walks sampled for BCG. And we see that we get almost 1,000x speed up by recomputing from scratch, as opposed to maintaining random walks. So now you may say that what I did in the previous experiment is not fair because I'm using L1 error, and this was tailored to my algorithm. While at the same time, BCG is also giving me multiplicative error, which is a harder thing to do. And it's actually a fair point. We also considered it. So we also looked at an error measure inspired by applications. So so we essentially we looked at how good these algorithms are in identifying vertices of very large PageRank. This is an error measure which none of the algorithms is designed for. In the interest of time, let me skip the precise definition and just show the result. Well, the bottom line is that the advantage is smaller, but we still see a good speed up at the same quality of the simple recomputation approach. One other thing is that you may wonder, because we recompute from scratch periodically, you may wonder, well, maybe the error is terrible every now and then. Again, yes, it can be bad, but compared to the BCG algorithm, is often much slower. And this is tuned such that the simple PageRank algorithm is actually faster in this case. The green line, in case you're wondering, is if we don't remember about the caveats that I mentioned in one of the first. OK, so the natural question, I think, Valerie was asking about that, is why is this so efficient?
Oh, yeah, the question. So these experimental results, were these for random deletions, or were these your snap graphs where you had actually real-world graphs?
We actually consider both random and temporal. They are not too far from each other.
Okay.
So the axes are temporal, circles are random. And actually, what you can see, I'm glad you asked, actually the temporal order, like the random order is something I always think of as being easy. The temporal order turned out to be easier than random, which I also found quite surprising. Thanks for the question. 2 minutes, so I'll need to rush a little bit. OK, so why is this batch recomputation so fast? Well, I think there are a few reasons. First of all, the recomputation algorithm is very efficient. Like we use power method, which is just like a sequential scan over edge array multiple times. That's great with respect to cache. We could also make it much faster using parallelization. We did not do that. That would probably widen the gap by another order of magnitude. At the same time, we saw that PageRank in reality changes slowly. Like the plots we saw there, I think that we can say that the temporal deletions appear to be even better than random deletions. So we saw that for random deletions, PageRank does not change by a lot. With temporal deletions, that's not any different. So that was not another reason why this worked. Well, we could essentially apply the results in some sense carried over from the random case. And on the other hand, the BCG algorithm has very large constant associated. We need to maintain a lot of random walks, and the algorithm is inherently cache unfriendly because of the random walks maintenance requires you to do a lot of random memory accesses. Also, in terms of space usage, I think there is like 100, if not 1,000x difference where the BCG algorithm uses orders of magnitude more space. OK, so let me sum up. So couple of open questions. One is that the BCG algorithm can be shown to handle fully dynamic updates in polylog n time if our graph is undirected. So that's a very strong assumption. And if we assume an oblivious adversary. Now, one question is, what about adaptive adversaries? We have not considered that. We know that maintaining perfectly random walks is essentially impossible. And we know, using what the technique that Touchable showed, that we can maintain a PageRank of a single vertex in roughly root n time. But we can probably get a decent approximation of PageRank using almost uniformly random walks. And the question is, can this be made to work? The second thought that I wanted to share is on using dynamic algorithms in practice. So when we develop theoretical algorithms, I think our objective is to have a good running time bound, good approximation bound. Well, we probably also want the write-up to fit in maybe 50 or 100 pages of PDF. This is like this is our limit on the complexity of the algorithm. But in practice, in practice, there is much more that an algorithm should satisfy in order to be practically implementable. Of course, it needs to be simple. We want to be able to implement it, but also test and maintain. So imagine you're like writing a TSP solver. You have a solution. It's actually very difficult to tell that the solution that you got is what you wanted to get. I mean, how would you test like if it's a good TSP solution? And this becomes even harder if the algorithm is very complicated. We want to be mindful about hidden constants. That matters a lot in implementation. Memory usage is also an important factor. Like, in fact, for parallel algorithms, this is the #1 limiting factor, the limiting scalability of the implementations. And it's something that we don't often care too much about. Good use of cache, and I guess many others. But my point is that, I think I have two comments. So first, for many of those, I think that people working on algorithms are most qualified to address. I think people who take an algorithm and want to implement it, they can deal with some of the challenges, but many of them, I would say that it's us, people working on a theory, that are best qualified to address. And the second point is that dynamic algorithms have even more requirements that they need to satisfy in order to be easy to use in practice. Like, we want a dynamic algorithm to be faster than we're computing from scratch, and it's not obvious in many cases, especially once we start comparing to some smart heuristics. There are other properties like history independence. Imagine you would like your solution to not depend on the sequence of updates that came, only at the edges that are in this current version. Because, for example, if you stop your algorithm, for example, to update implementation, you restart, you often don't want the solution to change dramatically. And history independence allows us to achieve that. So I think there is a lot of work that needs to go into making dynamic algorithms practical, and I hope that some of those may motivate some future work in the area. And then final thought before the wrap up is I was thinking that in the case of static algorithms, a lot of research went into identifying some useful properties of the graphs we work with. We know that real-world graphs are sparse. They have power law degree distributions, low diameter, and so on. But for update sequences, I'm not really aware of any assumptions that we may be able to exploit. Like, we sometimes study random order sequences, but I think we have very little understanding of what the actual update sequences are. And we know they matter a lot to how the algorithms perform in practice. Okay, so now this is really the final slide. I think, okay, I'm just one minute over. So just so to summarize, dynamic PageRank is quite easy under random updates. At the same time, maintaining multiplicative approximation in the worst case is provably hard. We can approximate it. We can give an additive approximation in amortized polylog time. But then at the same time, batch recomputation is a very competitive solution. We've seen empirical results. And then some open questions are, can we extend solutions to PageRank to adaptive adversaries? Can we maybe further improve batch recomputation with some kind of local tweaks between the recomputations? And more generally, how can we make dynamic algorithms easier to use in practice? I guess this may be a topic for lots of follow-up research. That's all I have. Thank you.
Thanks, Kuba. Happy to.
Yeah, just one quick question. So the lower bound that you mentioned for the multiplicative approximations was for 2 approximations. What about like larger multiplicative approximations?
I think that it may actually rule out any constant approximation as far as I remember the proof. So yeah, I think we actually, as I mentioned, I think we can make some variances like oscillate between a constant and 1 over polylog PageRank a large number of times, which will rule out any constant approximation. I can double check, but yeah, this is the best of my knowledge.
Thanks for the talk. So I have a question related to your point on static versus dynamic algorithms. So the static PageRank algorithm, it has much lower overheads because you don't actually need to store the random walks and you can just do like sparse matrix vector multiply. So I'm wondering at what point does the static algorithm actually do better than the batch recomputation algorithm? Like how large of a batch size do you need in order for the static one to actually do better and vice versa?
I'm not following.
I'm guessing like for large enough batches, you probably should just recompute it using the static algorithm, right?
I mean, what we do, okay, maybe let me clarify. When we have a graph, we got some number of updates, and our batch recomputation approach, I think, okay, I'm using batch in maybe slightly different way than what has been used before. When I get a batch of updates, I add all of those edges to the graph, and I run on the whole graph from scratch. I do not process the batch. I do not even treat the batch in any special way. I run on the whole graph entirely from scratch.
I see. Okay. And then you like the algorithm you run actually stores the random walks, right?
Well, no, the algorithm that I run up for once I add the edges to the graph, I use like the power iteration.
Oh, I see. Okay.
Yeah. So this is what's happening after every collection of updates.
I see. Okay. All right. Thanks.
Yeah. So this is exactly why this batch recomputation step is, as you point out, that's why it's so fast, because it's a cheap algorithm to run.
Thank you for the talk. I want to go to a meta point, building off your observation, which I very much agree, that we as algorithm designers are often in the best position to help make our algorithms practical. And it raises a question for me, how as a community we incentivize that kind of work. I think the standard response would be Allen X or SEA, but I think those are really focused on experiment and sort of the science of doing experiments, and I don't see them as perfect vehicles for incentivizing or giving great examples of that kind of work. So, I'd like to see the community start thinking about, or those in the community who really believe in implementations and in making algorithms practical, figure out some additional vehicles for that. SOSA is another step in that direction, but maybe there's another kind of step we can take as a community.
Yeah, thanks for the comment. I definitely agree. There is also ACDA, like a new initiative, which I think is also like on the intersection of theory and practice.
That's the systems.
ACDA?
Yeah.
No, this is not ICDE, but ACDA. That's. I think, Julian, you had students, right, who submitted to ACDA, right?
I think it's applied and computational discrete algorithms.
Yeah. So applied computation discrete algorithms. Okay. Yes.
Yeah, I heard what they were talking about.
Yeah, but it is like, from my perspective, it is difficult to even find proper venues for work that that has an algorithmic component and has an applied component. And part of the reason why the result is interesting is that it's applicable in practice. My feeling is that whenever we submit a paper, I have this feeling that either the reviewers would focus only on the empirical part or only on the theoretical part, and there are many cases where the papers are not going to be treated holistically. This paper, for context, is under submission to NeurIPS, which honestly, I don't think it's like a canonical venue where work like this could go, but yeah. But I do think, yeah, we may be, yes. So there are not a lot of venues where this works like this naturally belong to.
So I think this is a great discussion to take offline now, and I will close the session for now because we're already a bit over time. And please thank Kuba again. Thanks.